Hey there, it's Miss Heaton signing in to talk with you about a very exciting topic today. We're going to be dealing with nuclear chemistry. You've probably heard about nuclear chemistry somewhere else before, or at least nuclear things or radioactive things. So we're going to kind of get into the chemistry behind what exactly that means. So let's first start by defining what nuclear chemistry is all about. It's going to deal with the nucleus, and that makes sense because nuclear and nucleus have the same root word. We are not going to be dealing with electrons, so we're primarily concerned with the things here in the nucleus. We are not going to care about electrons. Now that's contrary or opposite to what we've been talking about all year long. All the reactions we've talked about so far deal with those electrons reacting. But today we are going to deal with the nucleus and its chemistry. Just to review, what particles will we find in the nucleus? Well, that would be the protons and the neutrons. Now, think back to when we talked about the nucleus. Why did we say it was a little bit weird that protons and neutrons, well, that protons especially, would be all together in the nucleus? What's weird about that? Well, remember that protons are all positive, and so we know that like charges repel, and so it's kind of weird that you have a whole bunch of protons crammed close together into this really, really dense, tight space called the nucleus. And so that's why we have the neutrons there. The neutrons are there to hide the protons from each other. In a sense, this is what I visualize when I say that. Here we've got a human shield. That is the neutron. The neutron is shielding these two angry protons from each other. So the neutrons are there to keep the peace. So you have to have a certain ratio of neutrons to protons in order to maintain the peace within the nucleus, to keep the nucleus from becoming unstable. So let's kind of relate this to radioactivity. You've heard that word before. You probably have some associations. Maybe you think of radioactive man or, people, mutants, I don't know, whatever you think of. Here's what I think of. And it has absolutely nothing to do with the fact that they are Asian or babies. That's probably not what you're actually thinking. The reason that I think of this is because this is a very unstable arrangement. Maybe some of these babies are neutrons, maybe some are protons, and this is our nucleus. This couch represents our nucleus. And notice that there's a pretty unstable arrangement of babies here. We've got some babies that look like they're about ready to jump ship. This one's about ready to slug this guy over here. So this is a very unstable couch. And in order to get stable, what has to happen is some of these babies have to leave. Only then will this couch be more stable. Some of those moms need to pull their babies off or they are going to fall off. So a radioactive nucleus is just like this. We need to get rid of some of these unstable pieces so that we get a more stable arrangement. And here's a graph that represents what a stable arrangement would be for different kinds of elements. This is called a band of stability graph. On the x-axis we have protons, on the y-axis we have neutrons. The dots here represent the stable region. So all these dots represent a band of stable nuclei. So let's label that the band of stability. And for certain elements, you need basically a 1-to-1 ratio. So like neon that has 10 protons would also need 10 neutrons. So for a total of 20 weight, or an atomic mass of 20. That's a 1-to-1 ratio of protons to neutrons. But if you extend that 1-to-1 line out, notice it goes straight like this, but the band of stability graph goes up a little bit. As the number of protons increases, let's take silver for example, you need somewhere between about 47 and, maybe 55 neutrons. So you need more neutrons than protons. And that makes sense, right? Because protons are very positive. The more of them there are, the more neutrons you need there to keep the peace between them, to keep them stable and nearby. So you have to have the right ratio of neutrons to protons in order to be stable. You don't need to memorize those ratios, but you should be able to read a graph and know what isotopes would be stable and which ones would not be. If an atom is outside of that neutron to proton ratio, for example, let's go with silver again. If you had a ratio that was like this, there was 40 protons and 70 neutrons, that would be unstable, and we call that a radioactive isotope. And it will give off either protons or neutrons to get back to a form of radiation. Well, it'll give off neutrons or protons as radiation, which we'll talk about in a minute, in order to get back to the right ratio. So in this case, maybe it would give off some neutrons, so it ends up back here, or maybe it would give off some protons or gain protons to get over here. Here are the three types of radiation. Here are the three types of radiation, and these are named before they actually knew what each particle was, and so they just named them alpha, beta, gamma after the Greek alphabet. So we'll go through each of the types and then use them in some reactions. So first of all, the alpha particle. This is a positively charged particle. We now know that it has 2 protons and 2 neutrons in it. So by giving off protons and neutrons, an atom can become stable. And if it has 2 protons and 2 neutrons, this is the symbol for it over here. Remember that this number at the top is protons plus neutrons. Hey folks, this is a great review for your final exam. So 4 protons and neutrons total, 2 protons. This number here is the number of protons. And we now know that something that has 2 protons is the helium atom. So basically, an alpha particle we now know is a helium atom with no electrons. Do you remember learning about an alpha particle back in our atom unit? These are the things that Rutherford shot through the gold foil to figure out that there was a nucleus. These are somewhat dangerous, especially if you eat them. If they get inside your body through your skin, they can cause a lot of damage. But your skin is able to stop them, so you don't have to be too worried about them. Here's an example of alpha decay. This found in your house. In your smoke detector at home, there's americium, and it gives off radiation, and if that beam of radiation is interrupted, then the fire alarm goes off. So americium decays by alpha decay, which means it gives off an alpha particle. So if it gave off an alpha particle, it would turn into Neptunium-237. So notice that in a nuclear reaction, we change the element because what's happening is the number of protons is changing. We go from having 95 to giving off 2 and having 93 left behind, and so that changes the element's identity by changing the number of protons. Also notice the mass number goes down by 4, going from americium to neptunium. Okay, type number 2. The beta particle. This is a high-speed electron, essentially. The symbol for it is 0 because it has a mass of 0 and -1 protons. Well, -1 proton, that would be an electron. The opposite of a proton is an electron. So essentially, this is an electron that has a lot more energy than a normal one. It can penetrate through your skin, so these will not be stopped just by having skin on. But they won't cause as much long-term damage as an alpha particle, so you don't have to be quite as worried about that. Beta particles are used in carbon dating, and this is not when carbon asks the neon out. This is when we use the isotopes left in a really old thing to figure out how old it is. So the carbon-14 is a radioactive isotope of carbon, and over time it will give off beta particles and turn into nitrogen. So notice that the mass number does not change because a beta particle doesn't weigh anything. It doesn't have any protons or neutrons in it. But it does change the number of protons because you have 6 protons before. This is basically a neutron turning into a proton and an electron. So this is -1, and so this has to become 7 because 7 plus -1 is 6. So you can look at the ratio of carbon-14 in the compound or in nitrogen, or the ratio of nitrogen in your old thing, and based on what that ratio is, what % of the total it is, you can figure out how old an object is. And finally, our third kind of radiation we're going to talk about today is the gamma ray. And this is the Greek letter gamma. It kind of looks like a Y. And it doesn't weigh anything, and it doesn't have any protons or electrons. So essentially, it's just light. It's a high-energy photon. This is the one that can go through just about anything, so you can't really avoid it. But the good news is that it is not very damaging. It doesn't cause a lot of negative effects. And I had a hard time finding an example of this, but there are some people up at Mayo Clinic that are using gamma knife surgery to do surgery on brain cancers. And so they can shoot gamma rays in there. And what gamma rays do here is basically it's not changing the element. So you maybe have cobalt that's like super excited, and you can get it to give off some energy, and it's still got cobalt at the end. So not super exciting reactions. We're not going to worry about those too much in our reactions. But I do want to tell you how you could stop each of these particles from getting to you. So let's say that someone was shooting an alpha particle gun. Doesn't really exist. But if they were shooting that at you, you could just hold up a piece of paper, and those alpha particles would be deterred. If you needed to get away from a beta particle, you would need to stand behind some thin pieces of wood. And if you were trying to get away from a gamma particle, you would need at least 3 feet of concrete or maybe some lead. So things that are very, very, well, very, very dense and very thick will stop a gamma particle. Okay, so let's figure out how we will use this. We're going to use this to write nuclear equations, just like chemical equations, but focused on the nucleus. And so we're still going to be using that isotope notation. So let's start with some more emission or decay reactions. So if we started with carbon-14, and it was going to give off an alpha particle, what would be left behind? Well, you're just doing some simple math. 14 equals 4 plus what? Well, that would be 10. And 6 equals 4 plus what? Well, that would be 4. And so then you'll use your periodic table. I'm going to flip to the periodic table quickly here. Oops, that's not the periodic table. There's the periodic table. Okay, and so we want to find the element that has 4 protons. In this case, that's beryllium. Oops, sorry guys, hang in there with me, we'll get this. Okay, and so that would be beryllium. Okay, try the next one on your own. And yes, you will need to find a periodic table to do that. Okay, now there's one other kind of equation we could have, and that's a radiation capture. For example, this, let's do the beta one this time. The nitrogen-14 atom could capture a beta particle and turn into something else. So let's see what it turns into. 14 plus 0 is 14. 7 plus negative 1, well, that's basically 7 minus 1, so that would become 6. So use your periodic table. Oh my goodness. There we go. The number at the bottom there was 6, so this would be carbon. That's carbon-14. Great. Folks, that is all there is to this first part of nuclear reactions. We will talk about more things later, but until then, happy radiating.